Over the past few decades, technology has advanced at a rapid pace, improving many aspects of our everyday lives. Traditional computers can solve complex mathematical problems using small switches called transistors. These switches can be either on or off. If the transistor is on, we can use it to store the number 1. If it is off, we can use it to store a 0. We call these ones and zeros bits.
But since most modern computers can only solve one problem at a time, the more complex the problem you want to solve, the more steps they'll need to take to do it. Some problems can be so complex that they'll need more computing power and more time than we can reasonably supply. These are called intractable problems. That's where quantum computing comes in, which relies on quantum bits, or qubits for short. But what is a qubit?
Well, a qubit is a way of representing information using quantum systems. While classical computers use ones and zeros, qubits can be a 1, a 0, or it can be both a 1 and a 0 at the same time, or an infinite number of values in between. Qubits can also store these values at the same time. This is called superposition, and it means that a qubit can contain much more information than traditional bits, making calculations much faster.
There are many different ways of constructing a qubit. One of them is to encode the quantum information in the electron of an atom, such as phosphorus. The electron can act like a simple magnet. It can align either with or against the surrounding magnetic field. When the electron is in the spin up state, it represents a 1, and spin down is a 0. To set up the spin state of an electron, we first cool it down to a very low temperature to stop the electron spinning uncontrollably. We then apply a specific frequency to set it into its quantum state. In reality, the qubit is constructed by placing a single phosphorus atom into a transistor.
To read the specific type of a qubit, we collapse its superposition, which puts it into its spin up equivalent to 1 or spin down equivalent to 0. If it's in its higher energy state, it will have enough energy to escape the atom and move into the transistor, leaving a positive charge which can be detected by the sensors as an increase in voltage.
Unlike in classical computing, qubits can perform 2 to the power of n number of calculations, where n is the number of qubits. Therefore, we can calculate that we only require 61 qubits to replace the whole of the world's computational power. However, in reality, to completely solve our problem, we need a chip with at least 10,000 qubits to calculate basic algorithms. After making some assumptions, we can calculate that we need about £8,000 for a single quantum chip. Naturally, it will be neither practical nor economically viable to replace all classical computers with quantum computers, since they are almost the size of a room and with today's technology are nearly impossible to build. But the groundbreaking fact that only 10,000 qubits could solve some of the most difficult problems that would take millions of years solving them by normal computers, could be processed in hours, opens up doors to a vast range of possibilities within technology. Imitating the behavior of atoms in unusual environments, such as inside particle colliders, improving the encryption of data, and simulating the effectiveness of drugs to cure epidemics, are just some of the potential uses of quantum computers on a large scale, benefiting stakeholders within scientific, business, and military industries alike.